All right. Today we're going to be discussing the application of these logic manipulations and that sort of thing in digital logic circuits. Combinations of signal bits, ones and zeros, can be transformed into other combinations of signal bits by means of various circuits. They are often seen as black boxes. The actual circuits vary depending on the technology used to create the logic circuit. So, how the transistors and all that stuff are connected internally is largely ignored, and it's the result of the inputs to the outputs that concerns most designers. A black box is a way of looking at different processes. It allows you to ignore the inner workings of a process and only be concerned with the inputs and outputs. Digital logic circuits are the same way. Different logic circuits are represented by their common symbols while the inner workings of the circuit are ignored. The black box is specified by constructing an input-output table that lists all the possible input signals together with their corresponding outputs. And got an example if you haven't seen one before. And then the output would be 1, 0, 0, 1, 0. Okay, so that is an example of what we in digital logic call a state table. This class refers to it as a variety of truth table. Just a little difference in terminology. State tables can have more than the two states represented here, so that's why they use state table in digital logic. For the purposes of this class, that we're only dealing with the two states, so it can be called a truth table. But the basic gates that you encounter, the NOT gate, or inverter, a circuit that inverts the signal for coming in. If it is a 1, then the output is a 0. If the input is a 0, then the output is a 1. The NOT gate has the truth table. Like so. And has a symbol, triangle with a bubble on it. What actually happens on the inside of an inverter is largely irrelevant. It depends on what type of technology, semiconductor technology, is being used to manufacture it, and can be largely ignored when you're doing logic circuit design. The AND gate is 2 inputs and has that for a truth table. If 2 or more input gates it has an AND gate has 2 or more input gates with 1 output. If all the inputs are 1, then the output is 1. If 1 or more inputs are 0, then the output is 0. So this corresponds to the tilde and the AND symbol here. Finally, you have the OR gate. Which has the 2 inputs and that symbol there. And that for a truth table. And that is corresponding to the OR symbol. 2 or more input gates with 1 output. If any of the inputs are 1, then the output is 1. If all the inputs are 0, then the output is 0. Using those 3 gates, you can implement any logic circuit that you want in some combination of the above gates. So rules for combinational circuits. Never combine 2 output wires. So say you have an inverter here and an AND gate here. That's a no-no. So no. This is bad. Because if this is high and this is low, that'd generate a short circuit. Things could catch on fire, start smoking, melting, that sort of thing. And we don't want that to happen in our circuits. So do not combine outputs into one output. A single input wire may be split partway and used as an input for more than one gate. So you can have one output feeding 2 inputs. That is okay. No short circuits will be generated by this if it were implemented. So that is okay. And obviously, an output wire can be used as an input. So the output of one can go into the input of another gate. And no output of a gate can eventually be fed back into that gate. Basically, basically, you don't want this. That type of circuit is used in sequential logic, but in combinational circuits, that is not allowed. So those are the general rules for combinational circuits. If you're given a set of input signals for a circuit, you can find its output by tracing through the circuit gate by gate. And I got a little example here. So we got OR gate, inverter, and an AND gate. And say these are P, Q, and R. That's your out. What you do is start your truth table. I'm doing this too big, but well, we can. I'll just go through part of it. Ran out of space. But you start with your first row. Put a 1 here, 1 here, 1 here. 1 ORed with 1 is going to be 1. That's going to invert it. And then 1 ANDed with 0 is going to be 0. So your output will be 0. Then you go through your next one. 1 1 0, 1 1 0. 1 OR 1 is going to be 1. Inverted is going to be 0. 0 and 0 is going to be 0. Yeah, see how that works? 1 0 1. 0 1. 1 OR 1. 1 OR 0 is 1. 0. 1 OR 1 and 0 is going to be 0 again. Not much variety going on here. But finally we have 1 0 0 and gonna have the same output there. Gonna have 0. Yeah, just trace it through step by step through the circuit to get your output list. Let's see here. Let's do something a little more simple. We got P. Oops. P or uh, not Q. P or Q, P or 1 or not 1 or 0 will be 1. P 1 or 0, not 0, which would be 1, would be 1 as well. And then P or not 1 would be 0, which would be 0. And then 0 and not 0 would be 1, which would be 0 or 1 would be a 1. Yeah, so pretty straightforward. I know I did this before. A show of hands, who has taken digital logic before? Okay, so this is all review and old hat to you. Now, a Boolean expression corresponding to a circuit. An expression composed of Boolean variables and connectives and or a not is called a Boolean expression. Find the Boolean expression for the following circuit. Let's see here. P and Q. And we're going to do or them and them together. Invert that. And that's going to and that. What is the Boolean expression corresponding to that? Well, you trace through the circuit from left to right, indicating the output of each circuit. Well, you would have P or Q, because the P and Q. Oops, come on. P or Q ANDed with the inverse of P and Q. So the leftmost gates you would put in parentheses and work your way right and out of the parentheses. Let's see here. Let's see here. Now we have circuit corresponding to a Boolean expression. Work from the outermost part of the Boolean expression to the innermost part, adding logic gates that correspond to the operations in the expression as you move right to left, not left to right, in the circuit diagram. Construct circuit for the following expression. Not P and Q. Or not Q. You work from outer, so you would say you would have a OR gate with not Q, and you would have Q, an AND gate going in, and P, not P. So the not P here, the AND here, see how I got that? Kind of, sort of. But you work from the outermost part of the expression and work into the parentheses as you work right to left. So you start with the OR because it's the lowest priority. And is the last operation done? Place it to the extreme right of the diagram. Continue working backward in the order of operations to get the gates and their connections from right to left. Let's see here. I think that is the end of my notes for chapter 2, but there's one more section of chapter 2. So go home and now go to chapter 2, section 5. All right. And we're going to finish off the logic of compound statements with number systems and circuits for addition. Binary representation of numbers. Any integer greater than 1 can serve as a base for a number system. In computer science, base 2 notation or binary notation is of special importance because the signals used in modern electronics are always in one of only two states. The Latin root bi means 2. So, derive the binary notation for the integers from 1 to 9. Well, the first digit The first bit is the one's position. The two's position, 2 to the first power, is the second bit. 2 to the second power is the third bit, and so on. So you count up 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, etc. Now, what's going on here is you count up to the maximum number of the highest valued symbol in the system. In base 2, there's only 2 symbols, 0 and 1. So, like decimal, count up to 1. You start out with 0 and then you count to 1. You run out of symbols. You carry the 1 into the next column and roll over back to 0. So 1, 1, 0, 1, 1. Roll over to 0. That rolls over to 0, and the 1 is carried into the third position. Then 1, 0, 1, 1, 1, 0, 1, 1, 1, and so forth. A list of powers of 2 is useful for doing binary to decimal and decimal to binary conversions. These are the powers of 2 and the values of each position of the bits in the binary numbers. So 1, 2, 4, 8, 16, 32, 64, etc., etc. You will get to know these numbers pretty well through the course of your time here. They're very commonly used. Represent 110101 in decimal notation. Well, 1 in the ones position, 1 in the fours position, 1 in the 16s, 1 in the 32s. So 16 plus 32 is 48, plus 4 is 52, plus 1 is 53. So it should be 53. Yeah. Woohoo, I can do basic math. This is the way you would do it. 1 times 2 to the power of 5 for the 6th bit. 1 to the power of 1 times 2 to the power of 4 for the 5th bit. 0 times 2 to the 3rd. 1 times 2 to the 2nd, etc. Those are the values of the position. And then you just multiply them, or add the positions together. Represent 209 in binary. Well, you have you write 209 as a sum of powers of 2, starting with the highest power of 2 that is less than 209 and counting to lower powers. So you have 128 is less than 209, so you would have a 1 in that position. 209 minus 128 is 81, and 81 is between 64 and 128, so the highest power of 2 that is less than 81 is 64. So subtract 64 from 81, you get, what is that, 17? Which is 16 plus 1. So you have 1, 1, 0, 1, 0, 0, 0, 1. But repeated subtraction and knowing your powers of 2 help with that. For each power of 2 that occurs in the sum, there is a 1 in the corresponding position of the binary number. For each power of 2 that is missing from the sum, then there is a 0 in the corresponding position of the binary number. Thus, 209 is 11010001. Binary addition and subtraction. The computational methods for binary arithmetic are analogous to those of decimal arithmetic. The binary arithmetic, in binary arithmetic, the number 2, which is equal to 1, 0 in binary notation, plays a similar role to that of the number 10 in decimal. So, add 1101 and 111. Well, 1 and 1 would be 2, which you don't have in base 2, so you do a 1 and a 0 and carry the 1. 1 and 0 plus the 1 carried would be 1. Would be 0, carry the 1, and so on. You would end up with, let's see here, 1 plus 1 is 0, carry the 1. Adding 2 2's together results in a carry of 1, and 2 1's together results in a carry of 1 when binary notation is used. Adding 3 1's together also results in a carry of 1. So 1 plus 1 plus 1 is 11, or 1 1 in binary. So the addition can be performed as follows. 1 and 1 is 0, carry the 1. 1 and 1 is 0, carry the 1. 1 and 1 is 1, carry the 1, which is 0, carry the 1, and so you have 10100 for the sum. Subtraction, I really don't like the way they handle this in this book, but to each their own. So in decimal subtraction, the fact of 10 minus 1 is 9 is used. I hate these slides. It's used to borrow across several columns. Okay, for example, here you borrow from the left, the next column to the left, and reduce it by 1, and add 10 to the right column. Then do your subtraction. So in binary subtraction, it may also be necessary to borrow more across more than one column. When you borrow 1 from 1 0 in base 10, what remains is 1. So the subtraction can be performed like this, which is just a really inefficient way of doing things, but you learn a more efficient way to do subtraction in digital logic using what's called 2's complement, but we'll leave that for that class. Circuits for computer addition. Consider the question of designing a circuit to produce the sum of 2 binary digits, P and Q. Both P and Q can be either 0 or 1. And the following facts are known. Those are the additions of the two numbers. It follows that the circuit must have two outputs, one for the left binary digit, this is called the carry, and one for the right binary digit, which is called the sum. The carry output is 1 if both P and Q are 1. It is 0 if it is 0 otherwise. Thus, the carry can be produced using the AND gate circuit that corresponds to the Boolean expression P and Q. The sum output is 1 if either P or Q, but not both, is 1. The sum can therefore be produced by using a circuit that corresponds to the Boolean expression for exclusive OR, which is the equivalent to that expression right there. Hence, the circuit to add two binary digits, P and Q, can be constructed as seen here. The circuit is called a half adder and has the input-output table like so. Carry of 1 when they're both 1, and a sum of 0. 1, 1, 1, 1, and 0 for the both outputs if they are both 0. Now consider the question of how to construct a circuit that can add two binary integers, each with more than one digit. Because the addition of two binary digits may result in a carry to the next column to the left, it may be necessary to add three binary digits to get at certain points. In the following example, the sum in the right column is the sum of two binary digits, and because of the carry, the sum in the left column is the sum of three binary digits. Thus, in order to construct a circuit that will add multi-digit binary numbers, it is necessary to incorporate a circuit that will compute the sum of all three binary digits. This circuit is called a full adder. The addition of three binary digits results in a carry and a sum as well as the half adder. The operation of the full adder is based on the fact that addition is a binary operation. Only two numbers can be added at one time. Thus, P is first added to Q, and the result is added to R. So consider this. 1 plus 0 plus 1 is 1, 0. It's 1 plus 0 plus 1. The associative property. It applies to addition. So it does here. So you have a half adder feeding your sum into the next half adder, and then you OR the two carries together, resulting in this input-output table here. So that is a full adder. So two full adders and one half adder can be used to build a circuit that will add two three-digit binary numbers, PQR and STU, to obtain the sum WXYZ. This is illustrated in this figure here. That's called a parallel adder, or also it's called a ripple adder, because the carries ripple down through the result and take a take a discrete amount of time to get the result once all the inputs are valid. Parallel adders can be constructed to add binary numbers of any finite length. Okay, 2's complement and the computer representation of signed integers. Typically, a fixed number of bits is used to represent integers on a computer. One way to do this is to select a particular bit, normally the leftmost, to indicate the sign of the integer, and to use the remaining bits for its absolute value in binary notation. The problem with this approach is that the procedures for adding the resulting numbers are somewhat complicated, and the representation of 0 is not unique. A more common approach is to use 2's complements, which makes it possible to add integers quite easily and results in a unique representation for 0. Bit lengths of 64 and sometimes 32 are often used in practice, but for simplicity and because the principles are the same for all bit lengths, we'll just do 8, a bit length of 8. 2's complement for an integer between negative 128 and 127 is a, if a is greater than or equal to 0, and 2 to the 8th minus a, if minus the absolute value of a, if a is less than 0. Thus, the 8-bit representation for a non-negative integer is the same as its 8-bit binary representation. As a concrete example for the negative integer, observe that this process here is used to to convert negative 46 into binary. So that is the result here. For negative integers, however, there's a more convenient way to compute 2's complement, which involves less arithmetic than applying the definition directly. Write the binary representation of absolute value of a, flip the bits, switch the 1's to 0's and the 0's to 1, and then add 1 in binary notation. So that uses, let's see here, in binary 46 is going to be this number here, flip the bits, add 1, and then it is the same result as was obtained from the definition. The fact that the method for finding the 8-bit 2's complement works in general depends on the following facts. The representation of 2 to the 8th minus 1 is all 1's. Subtracting an 8-bit binary number from a from all 1's, which is all the 1's to 0's and all the 0's to 1's. So this little equation is true for any number a. Here's how the facts are used when a is negative 46. Uh, 46 in absolute value is this here. Switch the bits by subtracting it from 2 to the 8th. and then add 1, and then you get, because you subtracted 1 from here, you add 1 back, and it's 2 to the 8th minus the absolute value of negative 46. Because 127 is the largest integer represented in the 8-bit 2's complement system, and because 127 is a 0 with 7 ones, all the 8-bit 2's complement for non-negative integers have a leading bit of 0. Because the bits are switched, the leading bit for all negative numbers is 1. This shows it as in a number line. You can see that 0 is 0, and negative 1 is all ones, and so on, as it counts down to negative 128. To find the decimal representation of the negative integer given a 8-bit 2's complement, apply the 2's complement procedure to the given 2's complement, and then write the decimal equivalent of the result. So you get the decimal representation of this number here by flipping the bits, adding 1, which is 87, but that's the absolute value, and because it had a leading 1, it's a negative number, so you have negative 87. So, yeah. Addition and subtraction with integers in 2's complement form. Well, the main advantage of 2's complement representation for integers is that the same computer circuits used to add in non-negative integers in binary notation can be used for both additions and subtractions of integers in a 2's complement system of numeration. First, note that a minus b is equal to a plus negative b for all real numbers. Any subtraction problem can then be changed to an addition one. For example, suppose we want to compute 78 minus 46. This equals to 78 plus negative 46, which should give us the answer of 32. To see what happens when you add the numbers in their 2's complement forms, observe that the 8-bit 2's complement for 78 is the same as the ordinary representation. The 2's complement for negative 46 has previously been shown to be this. Adding the numbers using binary addition gives the carry bit in the 9th or 2 to the 8th plus 1 position, but if you discard it, you obtain 0, 0, 1, and 5 zeros, which is the correct answer in 8-bits 2's complement form, because since 32 is 2 to the 8th, 32 is that number there. General procedure for using 8-bit 2's complement to add two integers. To add in two integers in the range of minus 128 through 127, whose sum is also in that range, convert both integers to their 8-bit 2's complement representations. Add the resulting integers using ordinary binary addition, discarding any carry bit of 1 that may occur in the 9th position, and then convert the result back to decimal form. And hexadecimal notation. That would be done by now, but hexadecimal notation is even more compact than decimal notation. It is much easier to convert back and forth between hexadecimal and binary than it is between binary and decimal notation. Hexadecimal refers to base 16 notation. Hexadecimal notation is based on the fact that any integer can be uniquely expressed as a sum of numbers of the form d times 16 to the n, where n is a non-negative integer and each d is one of the integers from 0 to 15. The 16 hexadecimal digits, together with their decimal forms and for future reference, their 4-bit binary equivalents are given here. After a while of using these, you get to know them pretty well and can convert things fairly easily between hexadecimal and binary. Convert 3CF to decimal. Well, it's 15 times 16 to the 0th power, or 1, so 15. 12 times 16 to the first power, or 16, is 192. And 3 times 16 to the squared, is which is 256, is 768. So add those together and you get 975. To convert an integer from hexadecimal to binary, write each hexadecimal digit of the integer in 4-bit binary notation. And then just juxtapose the results. So B09F would be 1010 for B, 0000 for 0, 1001 for 9, and 1111 for F. So, yeah, it's just a simple substitution. To convert integers written in binary notation to hexadecimal, reverse this process. Note that the commonly used computer representation for integers uses 32 bits. When these numbers are written in hexadecimal notation, only 8 characters are needed. To convert an integer from binary to hexadecimal, group the bits of the digits of the binary number into sets of 4, starting with the right and adding leading zeros as needed to the left. Convert the binary numbers in each set of 4 into hexadecimal digits. And there you are. So convert that big number to hexadecimal. Yeah, 101, 1010, 1101, and 0100. So you'd have 9 here, 10 here, A here, I'm sorry, A. C, I believe, C here, and 4 there. I'm sorry, D. Yeah, D. 4DA 9. So you add the leading zeros to make it an even group of 4, and convert each group of 4 bit digits bits to a hexadecimal digit. Then juxtapose the hexadecimal digits. The smallest addressable memory unit on most computers is 1 byte, or 8 bits. In some debugging operations, a dump is made of memory contents. That is, the contents of each memory location are displayed or printed out in order. To save space and make the output easier on the eye, the hex versions of the memory contents are given, rather than the binary versions. Suppose, for example, that the segment of memory dump looks like this. What is the actual content of those 4 memory locations? Those. Just simple substitution of the hexadecimal to binary. And that is it for Chapter 2. We will have a test on Chapter 2 and 1 on Thursday. So have your notes prepared for that. Homework is due before the start of class on Thursday, so keep that in mind. I think that's about it. I guess have a good day and see you on Thursday.